Very good afternoon, class. Welcome to our next lecture of Metallurgy and Material Sciences. In this lecture, we are going to discuss about various types of plain carbon steels and various types of cast irons. In previous class, we have discussed about the very most important topic in our Metallurgy and Materials, that in Unit 3, that is iron carbide diagram. In that, we have discussed about various eutectic points, eutectite points, protectic points, protectite points. So similarly, basing on that iron carbide diagram, we have splitted the iron into various categories, that is with the combination of the alloying of carbon. So we can make the iron into two types that we have already discussed. If we are adding the carbon from 0 to 0.8 percentage, so the carbon will be in the form of a steel. If it is in between 0.8 and 0.8 to 2.1, then it is called as hyper steels. If it is beyond 2 to some 4.6, 4.3, we call it as a cast irons, or still till 6.67 you can even call it as a cast irons. So the primary constituents of many of the plain carbon steels is iron and carbon. So what is a plain carbon steel is nothing but, so it can maximum have 1.5 percentage of carbon. Along with that, there are few small proportions or small elements like silica, sulfur, phosphorus and manganese can also be added to that. So but whereas when you compare these other elements like silicon, phosphorus and magnesium, they will be in much more less quantity. Okay, so they are generally available in the nature because of natural things, they are going to be added. So generally trying to add only a carbon with the iron particle. So they can be usually classified only if the applicable does not have a more strength. So in generally they do not have the more strength, and they are generally not used for any of the engineering applications. So classification of carbon steels. So carbon steels are mainly three types, that is one low carbon steel, one is medium carbon steel, another is high carbon steels. So low carbon steels are nothing but if it is having a percentage of 0.02 to 0.4 or 0.25, generally we call it as up to 0.25, we call it as a low carbon steel. So how they are obtained is containing carbon up to 0.25% respond to a heat treatment, as it improves the ductility property of the material, but whereas the strength of the iron will not be improved. So there cannot be improved either in the strength or the hardness of the material by heat. This is due to the lack of carbon, because carbon, as you know, that carbon is one of the hardest material. If you see diamond is one of the form of carbon, whereas graphite is also one of the form of the carbon. Because of the carbon various arrangements of carbon, we can able to make the carbon hardest, but whereas in low carbon steels, because of availability of less amount of carbon, it will be having less strength. So the microstructure, if you see, there will be more amount of ferrite than compared to that of the perlite. What is ferrite? We have already discussed. Ferrite is nothing but the alpha form of a iron, which is in the shape of a BCC structure. Whereas perlite, what is perlite? Perlite is nothing but a mixture, eutectic mixture of what? Both ferrite and as well as Fe3C. Fe3C is nothing but your iron carbide or cementite. So which is having less amount in this structure. Because of this, the strength of the material will be much less. They are relatively soft but have an extraordinary ductility, means they will undergo some kind of plastic deformation. Okay. Next, this is the microstructure. If you see, the most of the particles are nothing but your alpha iron, that is nothing but ferrite, whereas those black patches which you observe, so that is nothing but your perlite, that is nothing but your Fe3C. Okay. So what are the applications of this? If you generally see this, these are generally used in automobiles, refrigerator bodies, cans, like sheets, structural shapes, etc. Their applications also includes nails, nuts, bolts, boilers, plates. So these are generally made by using low carbon steels. These are the few examples. Okay. Next is medium carbon steel. Medium carbon steel is from 0.3 to 0.6 percentage of carbon. So they exhibit better percentage or better performance comparing to that of the low carbon steel when comparing that heat treatment process. So generally their mechanical properties will be much more improved when compared to that of the low carbon steel. They will be having more hardened nature because of the heat treatment process. By adding the alloy, their ability to get hard will be improved. Okay. So this is the medium carbon steel. If you see this is having a large amount of carbon in it, that is nothing but the carbon will not be existing as an individual particle, but whereas it will be existing as a Fe3C, that is nothing but iron carbide, okay, as you generally call it as a cementite also, okay. So application, these are generally used in gears, levers, cams, because these will be having much more strength comparing to that of like screws, nuts, bolts, etc. Okay, so this will be having much more hardness or much more strength, and they have to withstand large amount of loads like railway couplings, even railway barrels, so rifle barrels, ball millings. These are generally made because using medium carbon steel. Next is high carbon steel. High carbon steels are nothing but HCS steels, which are generally having 0.6 to 2%. We have already discussed 0.6, 0.0 to 0.8. We call it as hypo steels. Hypo steels are both what? Like your low carbon steel as well as your medium carbon steel, both are called as hypo, whereas hyper steels are nothing but your high carbon steel, which is in the from the percentage of 0.6 to 2. So these are the hardest and the strongest among all the plain carbon steels, like low carbon steel and medium carbon steel. They have a pure formability. Formability is nothing but we cannot be easily made this to a particular form. They cannot be easily machined, means they will be having a large amount of strength, so that we cannot able to machine them. Machine them means we cannot able to make them in our required shape. Even it is difficult to melt these kind of steels, that is high carbon steels. The alloying elements such as tungsten, molybdenum, chromium and vanadium can be added to these steels to form hard and wear resistant carbon compounds. So these alloys elements can also be added to this. These alloying elements, what are the effects of these alloying elements like tungsten, molybdenum, chromium? These things we will again study in your 4th unit. That is nothing but your alloy steels. So how these alloying elements will improve the strength of the steel, that we are going to discuss in our next chapter. Okay. So with to this chapter we will just understand how the high carbon steel will be harder, more machinable or more strength because of the percentage of carbon in it. So this, if you observe the microstructure of this high carbon steel, it will be much more large amount of carbon in the form of Fe3C is present. So what are the typical applications? These are used in springs, wrenches, cutting tools, dies, especially cutting tools. If you see lathe machine, HSSC steel, those steels are generally high strength steels. These are made because of by using high carbon steels only. Anvil, so anvil is nothing but your machine, tapes, razors, hacksaw blades. So these are having large amount of strength. Okay, these are generally made of high carbon steels. So what is the effect of this? This is generally again, what are the effects of these impurities like silicon, magnesium and sulfur? Again, these are we going to discuss in our next topic, so I will just skip this. So let us see what are the limitations of the plain carbon steel. So the strength of the plain carbon steels cannot be increased more than 700 megapascal. Okay, so without sustainability, loss in ductility or impact strength. They have a poor impact strength at the low temperatures. At low temperatures it can be easily broken. That means they can be easily broken. They have a poor resistance to corrosion. That is, I have already discussed that steel will be easily corroded by forming a oxidation. Okay, properties does not remain uniform for a larger thickness of plain carbon steels. If the thickness increases, it will not be isotropic, means it will not be uniform in all the direction with respect to that of the strength. Okay, whereas cast irons, what are cast irons? Iron carbon, actually if it is more than 2.1%, so these ions are generally called as cast irons. If from 0.2 to already I have studied discussed that in last lecture, that 6.67 can be maximum amount of carbon that can be added to a iron, that is cementite. Okay, so from 2.211 to above that, if you are adding the carbon content to the iron, so we can able to obtain cast irons. So it possesses the eutectic reaction during solidification. What is solidification? We are trying to change it to solidification. We have seen the eutectic point. So that is at a temperature 1147, we have observed that at this temperature 1147, we have observed that this liquid is completely converting into two solids, that is gamma plus Fe3C, where gamma is austenite structure, which is one of the hardest structure among the three forms of the iron. What are the three forms we have yesterday discussed? That is alpha ferrite, gamma ferrite and delta ferrite. Delta ferrite is generally most unstable nature, so it tries to convert to austenite structure. Austenite structure is one of the stable structure. Okay, so this point 1147, this is a eutectic reaction where liquid is converting into two solid structures. So typically the cast iron contains 2 to 4% of carbon and 0.5 to 3% of silica. So this silica will helps in maintaining the strength of the particle and able to maintain the resistive property, corrosion resistance. So enhances the oxidation and corrosion resistance, forming the tight adherence to the surface oxides. Okay. So this is yesterday we have seen what is this iron carbon diagram or iron carbon equilibrium diagram. Okay. So this we have yesterday seen in last class. So how the microstructure is going to change is, if you see in the cast irons, so especially when liquid, it is changed to austenite plus Fe3C. This both together we yesterday called it as lead burite. So similarly the liquid, when it is being when we are still cooling it, so at some temperature we can even able to obtain Fe3C and graphite. Graphite is one of the one of the form of the carbon which is not that much hard compared to that of the Fe3C. Okay. So this is one form. So graphene formation is slowly promoted. How this graphite is formed is slow cooling. If you are trying to cool, so this cooling is nothing but called as quenching. If you are cooling any of the material by heating to some temperature and you are trying to cool it either in the medium of water, either in the medium of air, either in the medium of natural cooling, then it is called as quenching process. Okay. So this slow cooling. So high carbon and silicon content. Okay. So in this we will be having high carbon and silicon content present. If both are high content, then graphite is generally formed. So heavy or thick section size, insulation particles, presence of sulfur, phosphorus, aluminum, nickel, tin, stanium, we call it stanium, manganese, cobalt, that is currum. Currum is nothing but gold, cobalt, antimony. Antimony is tin again. So the formation of cementite is favored by fast cooling. So these two are showing that when graphite is formed, when cementite is formed. If you are trying to cool faster, then cementite is formed. If it is having low percentage of carbon and silicon, then it will be forming ferrite. If it is having high carbon and silicon, then it will form graphite. So thin sections, if the element is thin section you are trying to form, then it is cementite is formed. So allying elements like titanium, vanadium, zirconium, chromium, manganese and molybdenum will be added to this cast iron. So there are various types of cast irons generally we see. So what are the various types of cast irons generally observed are grey cast iron and white cast iron. So from white cast iron again we can able to obtain malleable cast iron, ductile cast iron and compacted graphite iron. So compacted graphite iron is nothing but in this the graphite will be compacted into small natures like needles. So we even call it as a spherical spheroidal graphite cast iron, SSG graphite cast iron we call it. Okay. So I will show this all things in further slides. So if you see generally the presence of carbon will be present. If you see in the initial stages in the grey cast iron, the graphite is present in a half flake. Flakes is nothing but thin lines. So if you still make the material from grey cast iron to white cast iron, so it will be like a dispersed in the material. So perlite is nothing but it is completely dispersed in the material. If you are trying to make it to again the malleable cast iron, so in malleable cast iron what is happening is there will be the graphite noodles. Noodles means it will be like small structures will be formed in it. So when these structures are again heated or cooled, so basing upon the cooling, so it will be formed in the form of a spheroids, that is spheres. So spherical structures will be formed. So this will be when you see that they will be forming a compacted vermicular, that is nothing but if it will be arranged in particular sections. Okay. So the grey cast iron is the least expensive and most common type of the cast iron existing. So it is characterized by the formation of graphite. We have already discussed when graphite is formed when you are trying to cool slowly. So same this liquid cooling, this liquid that is the combination of iron and carbon, or when it is being cooled at 1147 degrees centigrade, if we are cooling at a low temperature or we are trying to cool it slowly, so then grey cast iron is generally formed. This grey cast iron is one of the most common type of cast iron. So it is characterized by the formation of graphite. So what is the typical composition is nothing but it will have up to 2.5 to 4% of carbon. It contains small interconnected graphite flakes. Interconnected means they will be slowly connected. Some of them will not be completely connected. Okay. So because of this they will be having low strength and ductility, because grain boundaries will be weak in this, so the material can be easily broken. So it is most widely used cast iron. It is named under dull gray color of the material when it is being fabricated. So when when this type of iron is cast iron is formed, so the color of the cast iron will be almost like a gray color, so we call it as a gray cast iron. So what are the properties? High compressive strength, so it can withstand large amount of strength. Good machinability, it can be easily machined in any of the machines. So good resistance to sliding wear. Sliding wear means because of the presence of chromium or silicon, what is the nature of this is it is able to withstand the wear of the material, so it will be easy to resist. So good resistance thermal fatigues, so thermal temperatures can be easily withstand. Good thermal conductivity and good vibrational dampings. So applications where are these generally used is generally damping vibrational energies are used. Because of this damping vibrational energies, so these are generally used in making of the beds of the any of the machines. Like if you are having a lathe machine, the bed of the lathe machine will be generally made by using a grey cast iron, because it can withstand large amount of vibrations. So that they have given here. So you can observe this in this slide. So they have highlighted this. So where it can be used is gears, flywheels, water pipes, and especially in machinery beds. Most of the machine beds are generally made of grey cast irons. So these are the various parts which are generally made by using grey cast iron. So these are nothing but your engine blocks. Okay, these are your engine blocks. This is your engine casing. Okay, these are the various parts which are generally made in your grey cast iron. Next is white cast iron. Like after grey cast iron, white cast iron is generally formed, which contains large amount of Fe3C. So it is one of the hardest material comparing to that of the grey cast iron. So the fractured structure of this white cast iron appears to be white. So when you are trying to break the cast iron, it appears to be a white nature when it is seen inside the cast iron. For example, if it is in the form of you are made it into a form of any of the shape. So if you break that shape, if you see inside, there will be a white color patches present in that. So basing on that white color, we have given the name it as a white cast irons. So this feature is low carbon equivalent is present, that is almost 1.8 to 3.6. If you see in this, it is 2.5 to 4. So low amount of carbon is present in it. Okay, and this is generally found when you are trying to cool it rapidly. Rapidly means at a fast rate of cooling. Okay, generally if you are trying to cool an object in the open air, it is slow cooling. If you are suddenly taking some bowl and you are trying to keep it at deep freeze, so because of low temperature, it will try to cooler at a faster rate. So the group of high alloyed white irons are generally used for their hardness and resistance to abrasive wear. So where they are generally used? They are generally used in brake shoes. Brake shoes means you are what do you say? You can see some of the brake shoes in your metallic natures. So stop blasting nozzles and like pump impellers. Pump impellers are nothing but your centrifugal pump impellers, like turbine impellers, like that. So wear resistance, they will be having much more wear resistance. So they are used in your ball bearings. Generally, white cast iron is used as an intermediate in the production of another cast iron, that is malleable cast iron. White fracture surfaces are formed. So no graphite, because carbon forms Fe3C are more complex carbides. So generally in this there is no graphite nature present. So this graphite will be converted as Fe3C in this because of fast cooling or rapid cooling. So malleable cast iron. So what is malleable cast iron? So malleable cast irons are formed when the heat treatment process is in the range of 900 degrees centigrade and unalloyed percentage of 3% carbon, whereas in the previous case we have seen it to be 1.8 to 3.6. So 3 and white unalloyed 3% carbon white cast iron. Okay, the cemented dissolves. So the cementite which is present in the white cast iron dissolves and forms in the form of a graphite clumps. Clumps is nothing but groups or nodules. It exhibits the better ductility than grey cast iron or white cast iron. Ductility means it will undergo large amount of plastic deformation comparing to that of the grey or white cast iron. Okay, and it is easily machinable. It can be easily machined in any of the machine. So the production steps, how this is generally produced? So it is produced in two stages. First is graphitization. Next is second stage of graphitization is making it into a ferritic malleable iron. So in first stage what we are going to do is the ferrite, that is nothing but Fe3C present in the white cast iron, we have to convert it into in the form of a graphite. The cementite which is present in the white cast iron will be decomposes to a stable austenite and graphite phases. So it is dissolving into two, that is austenite and graphite phases. So in second stage, when you again trying to cool it slowly, because it is a rapid cooling, here we are trying to make it slow cooling through an eutectide point temperature, eutectide temperature. What is this eutectide temperature? In one solid converting to two different solids. So through eutectide temperature to make it ferritic malleable ion. So this is the nature. So how it is going to become. Okay. When austenite is cooled in air or oil, ferritic malleable ion is obtained. So when you are trying to cool in open air or in the form of iron, so it is forming a ferritic malleable ion. So which is having a drawing is a heat treatment, the temperature that martensite or spheroidize the perlite. So spheroidizes the perlite is nothing but it will make the clumps of the what graphites. So if you see this is your air quenching, this is your slow cooling. So when you are trying to cool, this is your cast iron, that is white cast iron. When you are trying to cool it slowly, so when it is trying to cool in this way, so here if you take from 10 hours to 30 hours if you cool, so it will form ferritic malleable ion. So which is having ferrite or ferrite, you can say ferrite. Whereas if you see this sorry, I will try to highlight this again. This will observe this. So this is your nature. At this, if you are trying to cool at a slow rate, so this is going to be formed. What is this? This is ferritic malleable ion, which is having alpha ferrite and cementite. Now if you see this, when austenite, that is gamma, is completely quenched at a faster rate, that is at a time you are cooling it. So if you observe the difference between these two times, it is almost like 1 hour to 2 hours. If you are trying to reduce this temperature at a faster rate from 900 degrees to suddenly to 100 degrees centigrade, so because of this quenching and drawing, what is this drawing is, we are trying to change its structure by using various forms, various operations. So then we are going to observe a form, that is perlitic form. So in perlitic form, it will be having large amount of Fe3 structure. Okay. So the connecting rods, transmission gears and differential cases for the automobile industries, and also flanges, pipe fittings. Pipe fittings means like unions, like bends, wall parts, etc. Railroads are generally made using this. So next is ductile or nodular cast irons. So we have seen this ductile or nodular cast iron. So this ductile or nodular cast iron, this how it is formed. So this ductile or nodular cast iron contains spheroidal graphite particles. Spheroidal means it will be converted to in the form of a spheres. So previously it was in the form of noodles, now it is going to form in the form of a spheres. So spheres will be formed. How this is generally is produced? It is produced by treating liquid iron with carbon equivalent near to 4.3% with magnesium. So along with magnesium, it is generally formed. So what are the steps involved in this? Desulfurization. We are trying to remove the sulfur and oxygen present in the liquid. So nodulizing. So the magnesium which is present in the ductile form, that is MgFeSiLi, is added. So this adding will residual of 0.03 magnesium was present after the treatment in order to form the spheroidal graphites to grow. Next, this is a heterogeneous nucleation. Heterogeneous means different type of nucleations. Fading. The fadings occur by gradually non-violent loss of magnesium due to vaporization and reaction with oxygen. Oxygen vaporization means it generally reacts with oxygen. Reactions with magnesium which is present, it generally tries to vaporize or it tries to react with the oxygen. So inculcation of magnesium or both causes the graphite to form sphericulates. Sphericulates means it will try to make them spheres rather than flakes, also known as spheroidal graphites, SG. So that is nothing but nodular graphite ion. Next is compacted graphite cast iron. So this is the last type of cast iron. So the compacted cast iron, this what happens means the round cast spheroidal graphite which is present, that will be solidified, when they are trying to solidify, they will try to, during solidification, they will try to form, they will try to come all together in one particular place. So the intermediate between the flakes and the spheres with numerous rounded rods of graphites that are interconnected to the nucleus. So in the initial case, so they are in the form of a flakes, whereas in terms of nodular they will be in the form of a spheres, whereas in this, so it will not be in the form of a flakes, it will not be in the form of a sphere, but it will be in the form of a particular region where this flakes will be interconnected to one another. Okay, so vermicular graphite forms when ductile iron fades. So permits it permits a strength and ductility that exceeds more than that of the grey cast iron, but allows the iron to retain good thermal conductivity and vibrational damping. So when you are trying to do this from grey cast iron, when you are trying to obtain the compacted graphite cast iron, so it will have the same vibrational resistance property, but whereas its ductility will be reduced, but allows to maintain the thermal conductivity. Its strength will be exceeded compared to that of the grey cast iron, but whereas it's what we say thermal conductivity and vibrational maintaining nature will be same as that of the grey cast iron. So grey questions generally I have told that they are used in the making of beds of the machinery. So mechanical characteristics of the grey cast iron is less hard and brittle. It is generally less hard, whereas it is brittle in nature. Very weak in tension due to the point and sharp edges of the graphite flakes. So good during the compression, which graphite acts as a cushion or sponge. Okay, low shrinkage in mold due to formation of graphite flakes. So good dye bearing qualities due to graphite. So white cast iron is a composition which is having 2 to 4% and less than 1 respectively of silicon. So because of rapid cooling, so it forms a Fe3 structure, that is perlite and cementite. So the mechanical characteristics will be relatively very hard, brittle, whereas not weldable, not machinable. Okay, so when it is annealed, it becomes a malleable cast iron. Annealing is nothing but a process of cooling. Okay, the fracture structure of these alloys has a white appear, so it is called as a white cast iron. You can observe in the microstructure. So in this way, white patches will be observed. So these white patches are generally found because of the cementite. Okay, generally these are used in most of the railways, most of the machine beds, etc. Ductile cast iron. So this is the ductile cast iron microstructure. So if you see that because of rapid cooling, so this kind of nature is formed. Next, this is malleable cast iron. Okay, with this we can end our third unit. So if you have any doubts, please try to ask the doubts either in offline class or in the comment section. We will start our next class, that is fourth unit, from Wednesday most probably. Thank you.